This lesson we're going to be talking about graphing exponential functions. A function like y to the x power, where the base is a constant and the exponent is the independent variable, is an exponential function. So when x appears as the exponent instead of as the base or just as another term or anything like that, that would be when it's an exponential function. One type of exponential function is exponential growth. An exponential growth function is of the form f of x equals b to the x power, where b is greater than 1. So your base is a number that is bigger than 1, and your exponent is still x, or has x in it. The graph of an exponential function has an asymptote, which is a line that the graph of the function approaches but can't cross. So it's like a boundary. The asymptote for a function of the form f of x equals b to the x power is the x-axis, because if I raise a number bigger than 1 to any power, no matter if it's positive or negative, it'll never be a negative number. And this is all if we're not adding or subtracting outside of that b to the x power. That would move everything up or down. Domain is all real numbers, and then the range would depend on that asymptote. For the most basic function, it's y is greater than 0, but we'll talk about the range with each one that we graph. So example 1, graph 3 to the x power and state the domain and range. When your exponent is just x, the easiest way to do this is to just plug in -2, -1, 0, 1, 2. When it's like x plus 3 or anything like that, I'll talk about how to find the numbers to plug in. So we're plugging these in for x. So I have maybe 3 to the x power, so I'm going to do 3 to the -2nd. And personally, I would prefer to write these as fractions, but if you want to do decimals, that's okay. So 3 to the -2nd is 1/9. So then I'm plugging in 3 to the -1st. That would be 1/3. 3 to the 0 power, anything to the 0 power is equal to 1. 3 to the 1st is 3, and 3 squared we know is 9. So I'm going to graph this. -2 1/9 is really, really close to 0, but not quite 0. -1 1/3. 0 1 1 3 2 9. So exponential growth, really, really small increases at the beginning, but then eventually starts shooting up very, very fast. The domain is all real numbers. I could have plugged whatever I want in for x, doesn't really matter. My range has to do with my y values. I will never get a negative number because 3 to any power is always going to be positive. I'm also never going to get 0. I'm going to get really, really close to 0, but I'll never actually hit 0. So this graph is always above 0, so y is greater than 0. It's not equal to this time because y will never, ever be 0. No matter what exponent I have for 3, I'll never get 0 as an answer. The graph of f of x equals b to the x power represents the parent function or the parent graph of all exponential functions. So we've talked about different transformations. Remember, if you add or subtract inside the function, so in this case that'd be the exponent, that moves it left or right. So we talked about that with absolute value. If it was like x plus 1 inside the absolute variables, that moved to the left 1. If it was x minus 3 squared, that moved it to the right 3. Vertical, up or down, if you're adding outside of the function. So if we have the absolute value of x plus 3, that moved it up 3. The x squared minus 5, that moved it down 5. So if we're adding or subtracting away from that base to the x power. And then anything that we multiply by, that can either reflect it, like if it is negative absolute value of x or negative x squared. If we're multiplying by a number that has an absolute value greater than 1, like 3x squared stretches it. If the number is between 0 and 1. That's the value of that number, like 1/2. Excuse me. 1/2 times the absolute value of x. That was when it was compressed. So we're going to graph each function, state the domain and range. So our first one, we have y equals 2 to the x power plus 1, when our exponent is just x. We're going to do -2, -1, 0, 1, 2. I'm just going to type all these into my calculator. So I have 2 to the -2nd power, and then plus 1 outside of that exponent. I have 1.25. 2 to the -1st power plus 1, 1.5. 2 to the 0 power plus 1. 2 to the 0 is 1, plus 1 would make it 2. 2 to the 1st power would be 2. 2 plus 1 would give us 3. 2 to the 2nd power is 4, plus 1 is 5. So if I plot these, this is what my graph looks like. So domain is still all real numbers. Again, I can plug whatever I want in for x, it doesn't matter. My range, this time, my graph is getting really, really, really close to 1, but never actually going to hit 1. So this would be y is greater than 1. And the reason it's not 0 is because of this plus 1 here. This moved this graph up 1. Okay, b, y is equal to -1/2 times 5 to the x minus 2 power. So my exponent is x minus 2. I'm going to set that equal to 0. And if I add 2, x is equal to 2. I'm going to put that number in the middle of my graph. Or I can also think about this x minus 2 moves everything to the right too. So all my points move to the right. So -2, if I move it to the right, 2 would be 0. So on and so forth. So I'm going to put 2 in the middle of my graph. So 1 and 3, 0 and 4 would be the numbers I plug in. Or, like I was saying, -2 moved to the right, 2 is 0. -1 moved to the right, 2 is 1. 0 moved to the right, 2 is 2, and so on and so forth. So -1/2 times 5 to the 0 minus 2 power. Oops. You can stay inside the exponent for that. Maybe. On Desmos and on your graphing calculator, you have to use parentheses. I did forget about that. Desmos is tricky sometimes with that. Okay, so I type that in my calculator and I get negative 0.02, or as a fraction, -1/50. The only time I for sure do fractions is when it's a repeating decimal, like 1/3 is 0.3 repeating, so on and so forth. Okay, so now I'm plugging in 1 for x, so -1/2 times 5 to the 1 minus 2 power, -0.1. Plug 2 in, -0.5. Plug 3 in, -2.5. Plug 4 in, -12.5. So as you can see on my notes, my x-axis is in the wrong spot. I really need it to be up here. And we're going to ignore the fact that it's down here. I'll try to get that fixed on your notes before I print them off. So 0, -0.02 is really, really close to 0, but still not 0. 1, -1.1, really close to 0, but still not 0. 2, negative 0.5, 3, negative 2.5, and 4, negative 12.5. So if I go 3, 4, 5, 6, 7, 8, 9, I only have 9 boxes. I'm just going to put a point down here saying, hey, I know it's really far off the graph. But that way I get an idea of where to draw my line to. Domain is still all real numbers. We can plug whatever we want in for x when we make our table. I just showed you how to get the 5 best numbers to see the shape of your graph. This time the range is less than because it's always below a certain point, and our graph is approaching 0 but never actually going to hit 0. So we're less than 0 this time. You can model exponential growth with a constant percent over specific time periods using the function a of t is equal to a times 1 plus r to the t power. So the amount is a of t. T is the time period, so whether that's weeks, days, years, whatever. The lowercase a is the initial amount. So it's really confusing when we have an uppercase and a lowercase a. If you want to use y equals a times 1 plus r to the t power, that's fine. But the lowercase a is the initial amount. So whether it's a bacteria that you started with or money or anything like that. R is a percent of increase. It has to be written as a decimal. So 5%, 0.05. And then the base of our function is actually that whole quantity of 1 plus r, and that is the growth factor. The first U.S. Census was conducted in 1790. At that time, the population was 3,929,214. Since then, the U.S. population has grown by approximately 2.03% annually. Write an exponential growth function to represent this information, graph it on a graphing calculator. Okay, so we know that the U.S. population is growing by 2.03% annually, so that's our rate. We know the initial population from the first census is 3 million, blah, 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 that big number, that's an A there. And so we can write our function here. So we have A of t, or the amount as appeared as a function of time, is equal to 3,929,214 times 1 plus r percentage, 2.03% as a decimal, and move it to the left twice, is 0.0203 to the t power. And what's nice is you could use this function to then predict, hey, how many, what's our population now? What do we think it should be? So I could plug in how many years since 1790. If I graph this on a graphing calculator, y equals 3,929,214 times 1 plus 0.0203. I'm going to raise that to the x power. And this is what that exponential function would look like. So as you can see, our population is increasing very rapidly with this one. But if I said, hey, predict what the population would have been using this information in 1890, well, the first year was 1790. 1890 is 100 years after that. So you'd plug in 100 for t and type that into a calculator to predict that. The second type of exponential function is exponential decay. where f of x is equal to b to the x power. This time the base is a number between 0 and 1 instead of being a number greater than 1. So we graph them the exact same way. So if I have y equals 1/3 to the x power, I'm going to make a table. -2, -1, 0, 1, 2, because our exponent is just x. I'm going to type 1/3 to the -2nd power. That would be 9. 1/3 to the -1st power is 3. To the 0 power is 1. To the 1st power is 1/3. Squared would be to the 1/9 power. So -2, 9. -1, 3. 1, 0. So on and so forth. Look at this compared to the very first example we did. Notice that it's just reflected over the y-axis. So this time, exponential decay, we were decreasing very rapidly, but then eventually it slows down. Our domain is still all real numbers. Our range is y is greater than 0. This graph is always above 0. It's never actually going to hit 0. Y equals 1 times 1/4 to the x plus 2 minus 3 power. So we have x plus 2 as our exponent. If I set that equal to 0 and solve for x, that's what goes in the middle of my table. So -2 goes in the middle, so then -1, -3, 0, -4. Obviously that 1 in front of the parentheses, we really don't need that there because anything times 1 is itself. So I'm just going to focus on 1/4 to the -4 plus 2 power. I forgot my parentheses again. Minus 3. So I get 13. 1/4 to the -3 plus 2 power. Minus 3 is 1. 1/4 to the -2 plus 2 power minus 3 is -2. -1. No, 1/4 to -1 plus 2 power minus 3 is -2.75. 1/4 to the 0 plus 2 power minus 3, -2.9375. Okay, so if I graph this, -4, 13. I only have 9 boxes, so again, we're just going to estimate where that would be. -3, 1. -2, -2. We're going to have to do some more estimating here. So domain is still all real numbers. For our range, let's actually look at our table. Notice we were at 13, we shot all the way down to 1, then to -2, and so our decay rate is decreasing. We're getting really, really close to -3 here because we were at -2, then -2.75, then -2.9, blah, blah, blah. So y is always something compared to -3, and all of the numbers are greater than -3. Similar to exponential growth, you can model exponential decay. It's a very similar function, except for it's 1 minus r instead of 1 plus r. 1 minus r is the decay factor now instead of the growth factor. A cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of caffeine from the system per hour. Write an equation representing the amount of caffeine remaining after drinking a cup of green tea. So the amount of caffeine in their system as a period of time. The initial amount is 35 milligrams, so that's A, times 1 minus, they're eliminating 12.5% per hour. So 12.5% as a decimal, if I move it over to the left twice, is 0.125 to the t power. It's important to know that t is hours here, because we're given the percentage as, hey, they lose this percent per hour. So B, estimate the amount of caffeine in a teenage body's 3 hours after drinking that cup of tea. That's our time period there. Whereas if our time period was in days, we'd have to then convert it. So we're finding A of 3 for 3 hours equals 35 times 1 minus 0.125 to the third power. What's nice about scientific and graphing calculators, we can just type this in without even thinking about the order of operations. If you are using your iPhone calculator or anything like that, you would have to do parentheses first, then exponents, then multiplication. But I would just type this whole thing in at once, so that way you don't have any rounding in the middle. We get 23.45. So after 3 hours, there's 23.45 milligrams of caffeine in the average teen's body. All right, if you have any questions, bring them to class tomorrow or send me a text or an email.